This week we're covering Chapter 9, Greedy Techniques. Again, we're skipping Chapter 8 on dynamic programming. It's not that it's a bad chapter, it's just with the time that we have, I think this is going to be a better way to go, okay? And we won't be covering that one at all, okay? So this chapter is about greedy techniques. It's a way that when we're solving a problem, if we go for the most gain every iteration, it becomes a reasonable technique to solve some problems. Okay, so we're going to look through some examples here. So the first thing about this is for this greedy solutions that we're going to come up with, each of the steps that we take have to meet these criteria. Okay, so it has to be feasible. In other words, it has to be legal given the problem's constraints. It has to be locally optimal, which means of all the choices you're given at that particular point, it has to be the best one, okay? And it has to be irrevocable, which is important, that once you make it, you can't undo it. If you could undo it, then you're into some kind of lots more complicated algorithm, okay? So this is the idea. Again, you're going to grab the best alternative available in the hope that a sequence of logically optimal choices will yield a globally optimal solution, okay? So they give some examples here and things like this when we're placing 16 chips on not adjacent squares by being greedy and leaving ourselves the most available options. So we wouldn't want to pick here because then we've trapped the position here. So by picking in the corner, you then look and you go as close as you can get, which is going to be this one and it's going to be that one. And if you continue to do that, you'll find that you'll get more, the optimal number of chips on the board that meet that criteria, okay? And sometimes you have options. From this one, we can either take that one or that one, and you have to have a way just to arbitrarily decide on those, okay? So the next couple of sections, 9.1 and 9.2, talk about ways to figure out a minimum spanning tree. And I think these are probably terms that you may not be familiar with. So we'll take a bit to talk about it, okay? We're talking about graphs here, okay? So the graph has to be undirected, connected, and a weighted graph. Okay, so that's kind of what we're talking about here. So a graph, remember, is just a series of vertices or a set of vertices and a set of edges between them. Connected means you can get from all of the vertices to the other vertices. The weighted part means that each edge has a cost associated with it or a distance or whatever the time, whatever the case may be, okay? And undirected means that there are no arrows here, that AD and DA are both valid ways to go, okay? So that's the idea of the connected weighted graph, okay? So then a spanning tree then will be, more terminology here, an acyclic subgraph. Okay, so it's going to contain all of the edges. Okay, that makes it the subgraph. It's going to, all the vertices, some of the edges. Okay, and it's acyclic, which means you can't go in a circle. Okay, so for example, in this graph, A to C to D back to A is a cycle. Okay, so this one is not acyclic. Okay, this one is acyclic. Okay, so this then becomes a spanning tree of the first graph. Okay, so a spanning tree then is this connected acyclic subgraph that contains all the vertices. Okay, so you can have a spanning tree if you don't have a weighted graph, but if you have weights, then the minimum spanning tree is the tree that has the smallest weight. Okay, and this is going to have some applications, certainly in networking, when you're trying to move data around on a network to take links that are faster rather than slower. Lots of other areas where this comes into play. Okay, so the first algorithm we're talking about is called Prems Algorithm. Okay, and with this, the idea is we're going to start at some point. Okay, we're then going to take the next vertex, okay, that has the smallest weight, okay, and we're going to keep doing this, okay, so this is going to take us n-1 times to do that, okay, so I think this will make more sense with an example, but just look at some of the terminology we're using here, okay, So we start with the input to this. So the input is going to be a weighted connected graph. And a graph's always a set of vertices and set of edges. Okay. The output is going to be this E sub t, which is going to be a subset of the edges that composes the minimum spanning tree of G. Okay. So we're going to keep this V sub t as going to be the set of tree vertices that can be initiated with any vertex. Okay. And then we're originally setting this equal to just the initial one, okay, that we're at, the V sub 0, okay, and then we're setting this ET, that's the edges we're going to build originally at the empty set, okay. So then we're going to go from 1 to, this is the cardinality of V, or that's how many vertices you have minus 1. You've already got 1, so if you've got 10 vertices, you only have to do 9 of these, okay. We're then going to find the minimum weight edge, okay, among all the edges that you can do. Okay, so and we have this little v is in this set of VT, and little u is in the VT V minus those that we've already picked. Okay, so that's saying we're going to pick an edge that has not been picked already, or sorry, we're going to go to a vertex that hasn't been picked already. Okay, and then once we found that, then we're going to add this u, okay, the U star here to the set of vertices that we've used, okay? And then we're going to add the edge to that set of edges, okay? It's the edges that we're creating. This VT just keeps track that we've hit all the vertices, and the ET is the subtree or the spanning tree that we're building, okay? So again, I think it makes more sense to look at this with an example, okay? So here's an example at the top of the screen here of a graph. It's again, this is not acyclic. We have lots of cycles here. We're trying to find an acyclic spanning tree, but it is weighted, it is connected, okay? And then those little numbers there are the weights. So we're going to start at A. You don't have to start at A, but that's what we're starting in this case, okay? So we're then going to look at the remaining vertices that we have, okay? So from A, we can go to B with a cost of 3. We can go from A to F with a cost of 5, and A to E with a cost of 6, okay? So following the logic of this algorithm, the shortest path, or the least weight, is 3, okay? So we're going to fill in the edge here between A and B, okay? And now A was already in our V of T. We're going to add B to it, okay? And we're going to add the edge A, B to E sub t, okay? Then we're just going to keep going on. Once we've got the A and the B, from B, we're going to look at all the ways it can go. So we have B to C with a cost of 1, okay? We have B, we can't get from B to D, okay? So that's not, we saw that there too. You look at all the vertices that are not in V sub t, and sometimes you can't get to them. So again, just to hit that point, these two with the infinities here and the dashes means from A, we can't get to C, okay, directly, and we have no path following the dark lines yet, okay, and then we can't get to D either, okay. So once we have A and B, okay, we can get to C from A and B, okay. We can't get to D. We can get to E with our 6, and we can get to F, okay. So it says F here, B4, okay. So we're saying that from A to F, okay, we've already got this line. So we were now at B, so we can't go back to A. So we have to go from B, it's 4 more to get there, okay? So again, once you've hit A, you've moved on, and you're not going to go back to A, okay? So in this case, the smallest one is the C. So we're going to add, again, C to the VT, which means it has been selected, or it's been added to our spanning tree, okay? And we're going to add this edge BC to the E sub t, okay? So now we're at C. We have to look at what we can get to from C, okay? So from C, so we're down here, okay? So C, we can get to D with 6, okay? We can get to E. Oh, we still have, yeah, I'm sorry. We can still get from E from the A on the 6, okay? Because that wouldn't create a cycle, okay? And then we can create C to F, okay? So in that case, sorry, B is shorter. Okay, well, it doesn't matter. Go either way. And so you have to arbitrarily, they're both at 4. Okay, so we're going to pick this B to F, which is the 4. Okay, so then we're going to add F to our VT, and we're going to add the BF to the ET. Okay, so we're now at F. All we have left that are unattached are the D and the E. Okay, we have to think, how can we get to D or E from any point, any vertices that we have, again, not creating a cycle. Okay, so I can get here to D is my shortest way this way via F, okay, because this is shorter than those 3, okay, and E I can also get through from F with a cost of 2. So E's the winner there. So we make that one, okay. That leaves us just with D. Okay, and we can either do a C, D, an F, D, or an E, D, but the F, D is the one that is the shortest at 5. Okay, so you then add that. Okay, so the highlighted things here, okay, the darker lines are the ones that are the minimum of the spanning tree. Okay, so then there's some exercises there. Okay, then we get to the next section on Prems algorithm, which solves the same problem in a different way. Okay, so the basic idea here is that Prems is going to look for edges that are the smallest and add those in. Okay, so again, we're using the same basic terminology here. Okay, that we're setting up our number of edges equal to the empty set. We're going to use an E counter this time. Okay, and then we're going to set the number of processed edges to K. The K will work as the V sub T did before, and just that we're counting. Okay, so here's an example of this one. So we start with the same graph we had before. Okay, and we're going to sort the list of all the edges. Okay, so BC, for example, is the shortest edge. Okay, so then we go to EF and then AB and so forth. Okay, so that is the list of the sorted list of edges. Okay, and then we're going to start adding them from the left, from the smallest. Okay, as long as it's legal to do so. Okay, so as long as it doesn't create a cycle, and we're going to keep doing it until we have all of the edges covered. Okay, so this connects in a different way. Okay, so we add BC because it's the smallest. That's fine. The next one we add is EF. We've done that there. Yep, that's good. We next do AB. Okay, that's still okay. Okay. We then do BF. That's okay. Okay. We then do DF. That's next in order. Okay. And at that point, we've connected everything. Okay. So note that it's hard to get back up there, but we're getting the same minimum spanning tree. Okay. It is possible to have more than one minimum spanning tree, depending on the graph. I mean, you could have 2 spanning trees that end up with the same weight. For example, if all the weights were equal to 1 for some reason, then it makes you wonder why it's really a weighted graph. But in that situation, then you would have multiple ways to cover everything. Okay, so that's the basic idea behind Prems. And again, I think if you work through those examples, that will make more sense. This whole disjoint subsets and union find algorithms, you can just skip that. Okay, it's not something that I care about. Okay, that gets us then to my favorite computer scientist, his most famous algorithm. That's Dijkstra's algorithm. Okay, so Dijkstra's algorithm, as you're reading this the first time, it may seem that we're just doing the same thing again. Okay, and it turns out we're not. This is not a minimum spanning tree. This is the single source shortest path problem. Okay, so the idea here is from any source that you pick. Okay, so let's say you've got a graph that has an A. Start at A. What's the shortest path from A everywhere else? Okay, so this is very A-centric. Okay, this starts from one vertex. Okay, so we're not interested here, as it says directly, in the single shortest path that starts at the source and visits all the other vertices. Okay, that's a different problem. Okay, that's the traveling salesman problem. Okay, we're saying if you are at whatever vertex, how do you get to, if you're at A, how do you get to B? How do you get to C? Not B to C and back to A, just A to B, A to C, all those, okay? So again, the best known way to do this is through Dijkstra's algorithm. Okay, so here's the algorithm here. Okay, again, this is a similar kind of an algorithm as far as the way it looks here, that we're starting with a weighted connected graph G with our V and our E, and we have the non-negative weights. Okay, and it has a vertex S. Okay, so we're starting with a particular vertex. Okay, so the output then is going to be this dv and the shortest path from S to every other vertex, little v and big V. Okay, so we're going to initialize Q, which is a priority Q. Okay, we're then going to for every vertex V in V. Okay, so we're going to set the distance from our S to V being equal to infinity, and P, which is going to be the as it said here, is the penultimate vertex. So it's the vertex we're out at before we get to the one that we want, equal to null. Okay, and we're going to initialize that for all of the vertices. Okay. So we're then going to go through each time. Okay, and they use this super complicated priority queue thing, which we don't have to really mess with. We'll do this a different way. Okay, so this is one algorithm that, while I like it a lot, it's probably more than you want to understand line by line. Okay, let's look at an example. So again, in this case, we're taking this graph at the top. Okay, and we're going to keep a table here. So it's important that you can create this table. If there's interest, I may do an actual example of this on a separate video. In fact, I may already have a video. We'll see. So we're in this graph. A is where we're starting. Okay, and we want to find out the cheapest way to get from A to B and A to C and A to D and A to E. Okay, we're going to construct this as follows. We're going to start with A, and we're going to look at what's left. Okay, A getting to B. Okay, we're at A before we get there. A is the penultimate, and there's a cost of 3. C we can't get to at all. Okay, D we can get there. A again has to be the penultimate. That's all we have. A to D is 7. We can't get to E. Okay, so we would pick the B as the shortest one. Okay, we now have both A and B in our list. Okay, so we can look at the others. Okay, so I can now get to C. Okay, but unlike when we were doing it for Khrushchev's, the cost is not 4 because we're all from A. So we have to go from A to B, which is 3, and B to C, which is 4 more, for a total of 7. Okay, so that's where we get here. The C is the 3 plus 4. Okay, D, okay, we can get to 2 ways. We're going to take the minimum way here. We can go from A to D, which is 7, or we can go from A to B, which is 3, and then 2 more to get to D. So this is the preferred way. Okay, so that's A. We're always starting from A, but this is going, B is the one we were at before we get there, and that's the 3 plus 2 or a 5. Okay, with A and B, we still can't get to E. Okay, so we've selected this one now as part of our algorithm as the result of the shortest source path. Okay, shortest path to source, single source, shortest path. That's what it's called. Okay, so once we're here, okay, we have these two. We can now recalculate. Okay, we only have C and D to worry about. So what are the ways that we can get to C? Okay, we can go A to B to C, which has a cost of 7. We can go from A to B to D to C, which has a 3 plus 2, 5 plus 5 is 10. Okay, we still, we can get to E. Yeah, we can get to E. We can get to E, yes. We can get to E from A to B to D to E, okay, which is going to be 3 plus 2 is 5, plus 4 is 9. Okay, so the one we pick here then is to add the C. No, sorry, we've already added C. The shortest path there is the 9. Okay, so we're going to add the A to B to D to E, okay? So this gives us our final solution, okay? That if we wanted to get from A to B, we go direct. If we want to get from A to D, we go to B first and then to C. Then to D. We wanted to get to C, we go to B first and then to C. If we want to get to E, we're going to go from A to B to D to E, okay? And that becomes the shortest way to get to any of those points, okay? That's how that one works. Again, there's a different point you're trying to get to, okay? So the last section is interesting here. It's a Huffman code and Huffman trees and Huffman codes, okay? So if we're going to encode some text that's going to have some number of symbols, okay? And we'll refer to the alphabet as the possible symbols that we can have. So if you can have words that are created only from the vowels, okay, of the English language, then A, E, I, O, U would be the alphabet, okay? Normal English, we have the full letters we can do. Sometimes you have other things that you can do as well, okay? So if you want to turn this into a shorter code, you can use something like a fixed length encoding, which is what the ASCII code does, okay? So you create enough bits that you can cover the full range that you have, okay? So, but if you look at something like Morse code, okay, I'm not sure if you ever looked at that or not. That's little dots and dashes they used on the telegraph machines, okay? They had a preference for shorter symbols. So there's a variable length encoding, okay? So you have less storage on ones that are smaller, okay? So the letter E, for example, because it's used a lot, had a simple dot, the short note, okay? Where letters such as Q and Z, which aren't used very much, have 4 things that you use for them, okay? So with these variable length encoding, okay, you have to figure out a way to do this that actually doesn't leave you with decisions like which one to take, okay? So we're gonna limit ourselves here to the prefix free, okay? So no code word is a prefix of another code, so therefore you don't have to worry which way you're going, okay? So that's what we're going to create, okay? So again, I think that an example will make more sense, but we'll talk about this. So step 1 is to initialize in one node trees and label them with the symbols of the alphabet, okay? Whatever you have. These problems we're going to have limited alphabets just to avoid having to do these forever, okay? We're going to record the frequency of each symbol in its tree's root to indicate the tree's weight, okay? So to do this, we have to have some idea. So we have to know the known frequencies, okay? So you can look up for English what all the frequencies are in general. Or if you're doing a limited set, you would have to scan some data or somehow find that out, okay? So we're then going to repeat the following operation until a single tree is obtained. Find 2 trees with the smallest weight. If you have a tie, it can be broken arbitrarily, and make them the left and right subtree of a new tree and record their sums, the sum of their weights in the root of the new tree as its weight, okay? So let's take a look at an example. I think that will make more sense. So again, we have a limited alphabet. We have capital A, capital B, capital C, capital D, and the underscore, okay? And again, we know what the frequencies are. We know that A happens 35% of the time, B 10%, C 2%. That is not correct. C is 20%, D is 20%, and the dash is at 15%, okay? So the way we're going to do this, okay, we're going to start by putting in all of the frequencies in order, okay? So we start, the B was the lowest, okay? The dash came next, the C and the D, we arbitrarily put them in there, and the A is over here, okay? So this is from low to high, okay? The point being, as we build this tree, the lower ones get pushed down more, okay? So that's how this works, okay? So we start here that we have the 0.1 and the 0.25, okay, are going to be combined together, okay? Sorry, the 0.1 and the 0.15, okay, the B and the dash. So we're going to get a new node with a 0.25 because that's 0.1 plus 0.25, okay? That is here, okay? That is the tree with the B and the dash, okay? Now we create it over here, but now we have to sort it again. When we sort it again, it's now in the middle. So that's why this moves over to here, okay? We then look at the two lowest, no matter what they are. In this case, it's the two that are at 20%. We combine those into a new node, okay, with 0.4, okay, 0.2 plus 0.2 is 0.4. So we then resort, and the 0.25 becomes the smallest, and the 0.4 becomes the biggest, okay, with our C and our D, okay. We now look at the smallest being the 0.25 and the 0.35. We combine those together, okay, which is going to give us, that's going to be a 0.6, okay. So we now have levels here. The 0.6 points to the 0.25 and it points to the A, okay. And we have the 0.4 that's now smaller that points to the C and the D, okay. So then to get these two together, we get a 1. We're always going to get a 1 as long as our percentages, which they should, frequency should add up to 100%. Okay, so we have the 1 to the 4 and to the 6. We've combined them all together. Okay, what we're going to add here is a binary tree with 0 being left and 1 being right. Okay, we're going to assign that to each of these trees. Okay, we can now get this variable length Huffman coding based on this. Okay, so for example, if I wanted to get to C, it's a 0, 0. Okay, a D is a 0, 1. An A is a 1, 1. A B is a 1, 0, 0. And the dash is a 1, 0, 1. Okay, that gives you the following code. Okay, and at no point, so the 1, 1, we don't have to say, is it a 1, 1, 0 or a 1, 1, 1? Doesn't matter. There's only 1, 1, 1, right? So these are all unique. Okay, and this would be the code word for those frequencies. Okay, so here's an example. If we wanted to write the word dad, okay, the dad would be the D, an 01, the A, the 1, 1, and the D, an 01. Okay, so as we're reading it, we get to an O and a 1. So an O means it's either this one or this one. An 01 means that it's a D and we stop. Okay. We then get a 1, so it's either this one, or this one. Okay. Another 1, it's 100% that one. So there's the A, then there's the other D. Okay. And then if we decoded this, we start with the 1. Okay, so we know it's a B, or a dash. The next one's a 0. Okay. The 1, 0 is could be a B, could be a dash. The 1, 0, 0 we now know is a B. Okay. Then we get a 1. Okay, that could be several. A 1, 1 has to be an A. Then we get a 0, which can only be a couple. A 0, 1 is a D every time. Okay. A 1, 0, 1 is a dash. The 1, 1 again is an A. The 0, 1 is a D. Okay. So that's how this works. Okay. If we had to use a fixed length encoding for this, we would have to use at least 3 bits for each one. Okay. So in this case, we have 2 with 3 bits, but the other 3 only have 2 bits. Okay. So we can get this compression ratio here. Okay. So that's going to be the 25% here is how it's calculated. So it's the 3 bits that we were using for the other way with the 2.25, which is how many bits we're using when we get the average of all that we're doing here. Okay. Divided by 3 times 100% is 25%. So the Huffman encoding in this example will use 25% less memory than the fixed length encoding. Okay. So lots of experimentation has been shown that the compression ratio is typically between 20 and 80%. That's a pretty big range, but it depends on the characteristics of the text being compressed. Okay. So we talk about some other kinds of things here, but not really concerned about that. Okay. The Huffman code's all I'm looking for here. Okay. So that's the greedy techniques. Hopefully that will make some sense. Again, if you read through this and look at the homework, I'll probably post the homework tomorrow. and you're confused by it, I certainly do not mind doing an example of each of these in a little bit more detail. Okay, so let me know. Beyond that, we'll have our normal meeting on Thursday, okay, where we can discuss things and go through. And hopefully this will not be a huge homework problem set. I think it's relatively straightforward once you get your head around it. So hopefully you'll be able to get your head around it. Okay. So I want to get back up to the top for reasons that are unclear except for closure. So let's get back up here. And then we can stop. Sometimes being OCD is a bad thing. Okay. Anyway, so again, these are greedy techniques. They're techniques where we try to take the best locally optimal solutions, string those together to solve the entire problem.